modern physics topic, and this section is called Calculating the Energy of a Photon. A photon is a little particle of light. Now, photons, even though we think of them as particles, they do not have mass. But photons have momentum and photons have energy. And we're going to calculate the energy possessed by different photons, violet photons and red photons, using equations from our reference tables. What I'd like you to do is open your reference tables to the modern physics section. The modern physics section is right underneath waves and optics, right here in the middle. And copy down the equations. There are two equations for the energy of a photon. Actually, there's three, but we'll use the first two today. So, the energy of a photon can be calculated by multiplying h, which is a constant on the front page of your reference tables, times the frequency of the photon, or by multiplying h times c, the speed of light, over lambda, the wavelength of the light. Right now, I'd like to focus on this portion of the equation with using the frequency to determine the energy, and we'll do this part later using the wavelength to determine the energy of the photon. Now, on the front of your reference tables, you will find Planck's constant. On the front of the reference tables, toward the bottom of the top chart, where all the constants are, list of physical constants, here's Planck's constant, lowercase h. It is 6.63 times 10 to the negative 34. Right? H is 6.63 times 10 to the negative 34 joule seconds. Now that's not joules per second. That's power. This is joules times seconds, or joule seconds. It's not joules per second. It's joule seconds. All right, now, let's look up some possible frequencies for visible light. We can look those up on the chart called the electromagnetic spectrum. All right, so turn to that chart where we have visible light. All right, and on that chart, we see violet on the left side and red light on the right side. All right, you need to have the chart in front of you. All right, so violet light can have a frequency anywhere from 6.59 times 10 to the 14th to 7.69 times 10 to the 14th. So I'm going to pick a number in between these two that's nice and simple to work with. How about 7.00 times 10 to the 14th? So that's what I'll choose as my example today for the frequency of violet light. Now, you have violet, you have blue, you have green, you have yellow, orange, and red. And we're going to need a frequency for red light as well. Now, we've chosen for the violet, we've chosen 7 times 10 to the 14th hertz. For the red, we can choose anything between 3.84 times 10 to the 14th. Remember, I'm making up an example. On the Regents exam, they will probably give you specific frequencies or wavelengths to work with. But I'm making up an example right here, and I just want an example between 3.84 and 4.82 times 10 to the 14th for red light. I'm going to choose 4.00 times 10 to the 14th for the frequency of my red light in this example today. Okay, now that we have frequencies and we know Planck's constant, we can calculate the energy in a violet photon and the energy in a red photon. Let's do that. All right, here's the equation again. The energy of a photon is equal to Planck's constant times the frequency. All right, so Planck's constant from the front of the reference tables is 6.63 times 10 to the negative 34 joule seconds. And the frequency that we selected for our violet light is 7 times 10 to the 14th inverse seconds. All right, so we multiply these together. 6.63 second E negative 34 times 7 second E 14. And we get 4.64 times 10 to the negative 19. Now, what about the unit? Well, we've got seconds on top, seconds on the bottom. The seconds are going to cancel, and we're left with joules. All right, now, one important thing about this equation. Since Planck's constant is in joules, the energy that we get from this equation will always be in joules. And you can only put joules into this equation when you use this version of Planck's constant, which is the only version that we use in Regents Physics. There are other versions, but we will not be using them in Regents Physics. So you put joules in, or you get joules out. You're not going to get any other kind of energy, electron volts. You will not get, you can only put joules here, or you can get joules from this equation. If you want something else like electron volts, you're going to have to convert these joules to electron volts later. If you want to put electron volts into here, you can't. You have to convert them to joules first and then put them into this equation with this version of Planck's constant. So joules. Joules in, joules out. All right, now, the energy of our violet photon is 4.64 times 10 to the negative 19. I'll put that down here. Energy violet equals 4.64 times 10 to the negative 19 joules. Okay, now let's figure out the energy possessed by a red photon. Here we go. All right, a red photon. E equals HF. All right, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. The red photon, an example of a frequency that is red light, would be 4.00 times 10 to the negative, times 10 to the 14th, 1 over seconds. All right, we multiply those together. 6.63 second E negative 34 times 4 second E 14. And we get 2.65 times 10 to the negative 19 joules. That's the amount of energy possessed by a red photon of light. So, energy red times 10 to the negative 19 joules. All right? Now, right away, we see that violet photons have more energy than red photons. All right? Now, I'd like to use the other version of the equation. I'd like to use E equals hc over lambda. But I need the wavelength of violet light and the wavelength of red light traveling at c, the speed of light, in order to plug into this equation. So let's take the frequencies that we originally had and calculate what the wavelengths would be. Now, I will say that I do not like to use this chart here for wavelengths. This chart is very accurate with the frequencies on the bottom. The wavelengths are much less accurate. The wavelengths are much less accurate. All right, so I won't be using the wavelengths as I read them off the chart. Rather, I read the frequencies off the chart and I will be converting them to wavelength right now. Let me show you how that's done. We can use the equation V equals F times lambda. If we know, you don't have to shut the drawer. We can use the equation V equals F times lambda to calculate the wavelength of violet light and the wavelength of red light. All right, now, the speed of light would have to be c 3 times 10 to the 8th meters per second. All right, so we're trying to calculate the wavelength, so let's solve for wavelength. Wavelength equals, we're going to divide by frequency on both sides. Wavelength equals V over frequency. Velocity divided by frequency. All right? So, we're going to calculate the wavelength, velocity divided by frequency. Let's move him up and let's calculate the wavelengths. All right? V equals, wavelength equals V divided by frequency. Now, of course, this velocity is c, the speed of light, from the front of your reference tables. Right there, 3 times 10 to the 8th meters per second. So here we go. What is a common wavelength for violet light? All right, 3 times 10 to the 8th meters per second. The frequency that we had for violet light back at the beginning was 7 times 10 to the 14th 1 over seconds. So what would be an acceptable wavelength for violet light? Okay, 3 second E8 divided by 7 second E14. 4.29 times 10 to the negative 7 meters. All right, this is a wavelength for violet light. Now, what about the red? All right, a wavelength for red light, 3 times 10 to the 8th meters per second, divided by 4 times 10 to the 14th, 1 over seconds. 3 second E8 divided by 4 second E14 equals, all right, 7.50 times 10 to the negative 7 meters. Now, right away, you see that red light has a longer wavelength than violet light. But that makes sense, because there is an inverse relationship between energy and wavelength, just as there is a direct relationship between energy and frequency. So higher energy would be a smaller wavelength. Lower energy would be a larger wavelength. Okay. Now that we have a typical wavelength for violet light and a typical wavelength for red light, let's use that other equation. All right, making believe that we never had the frequency, we were given this wavelength instead. Let's calculate the energy of a violet photon and the energy of a red photon using the wavelength instead of the frequency. All right, so what if what if we were given the wavelength and asked to find the energy of the photon? Here's the other part of that equation. The energy of a photon is equal to hc over lambda. Now, I'm going to move my wavelength down here. I'd like to keep these energies because I'd like to prove to you that whether you use the frequency equation or the wavelength equation, you're going to obviously get the same energy. All right, this is two different ways to do the same thing. So, the wavelength of violet light, 4.29 times 10 to the negative 7 meters. All right, I can erase that. And the wavelength of red light, move that down, equals 7.5 times 10 to the negative 7 meters. Okay, now we can erase all this. All right, so here, I'm just keeping my important numbers handy down here. All right, here we go. So, we're given the wavelength of violet light, and we're going to find the energy of that violet photon. Planck's constant, 6.63 times 10 to the negative 34 joule seconds. The speed of light, 3 times 10 to the 8th meters per second. Remember, you're looking all these constants up on the front of the reference tables. All right? And divided by the wavelength of the violet light, 4.29 times 10 to the negative 7 meters. All right, now I tell you what, we can erase that. All right, we don't need him. All right? But we're going to hang on to this energy here. All right, now, this times this, 6.63 second E negative 34 times 3 second E8 equals, I hit equals, now I'm going to hit divided by this. Divided by 4.29 second E negative 7. All right, I'm getting 4.64 on the nose times 10 to the negative 19. I got the same amount of energy whether I calculated E using the frequency or I calculated E using the wavelength, which corresponds to that same frequency. All right, now let's do the red light just to be thorough. Okay, I know you're getting this, but let's do the red light just to be thorough. Okay, so, oops, you know, I really didn't need to erase that whole top there, did I? That's all going to be the same. All right, so H, 6.63 times 10 to the negative 34 joule seconds. 3 times 10 to the 8th meters per second. All right, divided by, here's the wavelength of red light, 7.5 times 10 to the negative 7. 7.5 times 10 to the negative 7 meters. Okay, so I don't need this guy anymore. Away we go. Put my negative 19 back there. All right. Okay. Let's do the math. 6.63 second E negative 34 times 3 second E8 equals, I'm going to divide, now I'm going to divide by 7.50, I just put in 7.5 second E negative 7. And I'm getting 2.65. Look, see? 2.65 times 10 to the negative 19 as the energy of the red photon. All right? Now, I'd just like to do one more calculation to show you how to handle electron volts. If you're given electron volts and you need to plug them into the equation. Now, electron volts are a very tiny unit of energy. An electron volt is an EV, right? Electron volt. All right, now, let's say, for example, that you're given a photon with 2.11 electron volts. All right, so the energy of the photon is 2.11 electron volts. And you're being asked to calculate the frequency of the photon. So you're given energy, you want frequency, so you select this equation, E equals HF. Now, you want the frequency, so you're going to say F equals E over H. But here's the problem. Your H, your Planck's constant, has the unit joule seconds. So you cannot use two different units for energy in the same equation at the same time. You have electron volts up here, and you have joules down here. So let's convert the electron volts to joules, then we can plug into this equation. Remember, this equation, joules in, joules out. All right? So, let me show you how to convert electron volts to joules. The conversion factor is on the front of your reference tables. It's, let's see, 1, 2, 3, 4, 5, 6. It's the sixth line up from the bottom. All right? On this top chart, it's the sixth line up from the bottom. It says 1 electron volt equals 1.6 times 10 to the negative 19 joules. Remember, look at the front of your reference tables right now while I'm doing this. So, 1 electron volt equals 1.60 times 10 to the negative 19 joules. Okay, now let's do this conversion. 2.11 electron volts. I'm doing a conversion, so I put a large set of parentheses. My equal sign is over here. I want to get rid of, now remember, the electron volts are on the top. See them on the top? I can put them over 1 if I want to. Now, I want to get rid of electron volts. So I put electron volts down here on the bottom. I want joules. And in the parentheses, this must equal this. Basically, the parentheses must come to a multiplicative factor of 1. This and this must be the same. Well, if 1 electron volt equals 1.6 times 10 to the negative 19 joules, then this and this are the same. As long as they're equal to each other, I can put them into the parentheses for this method of converting. This method of converting will work for you whether you become a doctor, an engineer, an accountant, whatever you become, a nurse, nurse practitioner, this pharmacist. This method of converting will always work for you no matter what you're converting. You need two things that equal each other. You put what you're given, put a set of parentheses. You can do a lot more parentheses as needed. A set of parentheses, top and bottom, must equal each other. Ready? Now, the electron volts, top and bottom, cancel. That's why I put the electron volts down here. And now, 2.11 times this. The equal sign is over here. You cannot cross multiply this. The equal sign is over here. It's 2.11 times 1.6 times 10 to the negative 19. If there was something on the bottom, we would have to divide. But we don't have to divide by 1, of course. It would come out the same. All right. 2.11 times 1.6 second E negative 19 equals. All right, we're getting for the energy in joules, we're getting 3.38 times 10 to the negative 19 joules. All right? So, now we can use the equation to find the frequency of that photon. We were given electron volts, we converted to joules, so we could use the equation E equals HF. All right, so here we go. I'm going to leave that number down there for just a minute. All right, here we go. E equals hf, so therefore F equals E over H. Now E is right here. 3.38 times 10 to the negative 19 joules. Planck's constant in joule seconds, 6.63 times 10 to the negative 34 joule seconds. All right? Now, let's divide those and get the frequency. Now, by the way, what do you think the exponent of the frequency should probably be, approximately? I remember some frequencies being 10 to the 14th. So maybe it should be somewhere, possibly around there. Let's see, 3.38 second E negative 19 divided by 6.63 second E negative 34 equals, and here we go, 5.09 times 10 to the 14th, and frequency would be inverse seconds. All right, these joules cancel, and we have seconds here on the bottom, so your unit is 1 over seconds. This is the frequency of the 2.11 electron volt photon. All right, now let's identify the color of this photon. What color would this be? Go to the electromagnetic spectrum chart, and 5.09 is in the yellow range. Yellow is between 5.03 and 5.20. So 5.09 is definitely yellow light. All right, so this is yellow visible light, or visible yellow light. The color is yellow. All right? Now, just a little summary of what we've talked about. If you want to calculate how much energy a photon of light has, there are at least two equations, the ones that we covered today. E equals HF, or E equals HC over lambda. Now, possibly you can see where C over lambda comes from. If you take this equation, V equals F times lambda, and the speed of light is C, and then we solve for frequency. All right, frequency equals C over lambda, right? Now, instead of frequency, over here, we can put C over lambda. So you see that this equation is really just a combination of this equation and our old buddy, V equals F lambda. So these are two equations on your reference tables that you can use to calculate the energy possessed by a photon of light. Now, class, these equations, since you're using Planck's constant, here, H, and the unit of Planck's constant for our purposes is joule second, you cannot put electron volts or any other unit of energy into these equations. Because Planck's constant has joules, you can only put joules in, or you can only get joules out. If you're given electron volts, convert them to joules and then put them in. If you want electron volts, get the joules and then convert them to electron volts. All right, and that about sums it up. All right, using the equation for the energy of a photon given the frequency or given its wavelength. See you in the next section.